Welcome to Study Loop.
Okay, so we're looking at a problem which involves a circuit with a series of resistors and capacitors. Now, this problem, it talks about two specific points in time, basically, when the switch is open and when the switch is closed. It doesn't really give us any information about in between. So when we're going to make some assumptions about when the switch is open, it has been open long enough to where the capacitor is fully charged, and when the switch is closed, it's been closed long enough in which the capacitors have become fully discharged. Now, the first part asks, what is the potential of point A with respect to point B when the switch is open? So when the switch is open, there's no current flow, basically, and since the capacitors are fully charged, they're at its maximum charge. So we use equation 26.11 from the text, which is the EMF, or the voltage, is equal to the I'm sorry, EMF over the resistance is equal to the total charge, QF, which is the maximum charge where the capacitor is fully charged, divided by the resistance times the capacitance, where QF is equal to the EMF times C, or the voltage times the capacitance. Please excuse my writing here. I will be getting a Wacom at some point to make this a little easier, but I'm just using a mouse. So now, if you plug in this EC for QF, and then simplify, you end up basically with just is equal to E, which in this particular instance is 18 volts, which is where the battery, the voltage of the battery. 18 volts. All right, so this is part A. Now, part B asks, I'll say this is equal to voltage of A with respect to B. Now, part B asks, which point is at a higher potential. Now, if you look at the circuit here with the switch open, the capacitor is basically a break in the circuit. There can be no current flow through that. So A is actually in direct connection with the positive terminal of the battery, which means that A is actually at the highest potential. So that's the answer to B. So it's a pretty straightforward answer. Now, moving on to C. We'll move on to C here. C talks about now the switch is closed. So we've closed the switch, which completes this circuit. So the circuit is now completed. The battery, the voltage here starts at 18 volts, and the current is allowed to flow through the resistors to the ground, the negative terminal of the battery. Now, when that is done, the current that flows through the circuit is using Ohm's law, which is, you know what? Let me write Ohm's law. B is equal to IR. And so I is equal to V over R, which in this particular instance is 18 volts divided by the sum of these two resistors, because they're in series along this path, 6.00 ohms plus 3.00 ohms, which is equal to 18 volts divided by 9.00 ohms, which gives a current through the circuit of 2.00 amps. Should put 0.0 on 18 to keep the significant figures. Now, So now the potential at point B with respect to ground, which is the question for part C, it wants to know what's the potential at point B with respect to ground, or the negative terminal of the battery here. So that's just going to be, so we now know the current in the circuit based on using the current flow through the two resistors. So we can now say, so I'll come down here and say, so V is equal to IR, which is equal to 2.00 amps, bang, times 3 ohms, because that's the only resistor between B and the ground, 3.00 ohms, which is going to be equal to 6 volts. So that is the potential of B with respect to ground. Okay, so now moving on to part D. This is a little bit more involved. So now wants to know what is, so how much charge on each capacitor. So how much? What's the charge? What's the difference? How much charge does the capacitors lose when the switch is closed, basically? So when you start, so let's first look at the charge on each capacitor when the switch is open. So that's going to be the maximum charge. So now we'll call this guy capacitor A, and then this guy capacitor B. All right. So the charge, the initial charge on capacitor A is going to be equal to the capacitance times the voltage, which is now equal to, so the capacitance is given as A is 3 microfarads. So 3.00 times 10 to the minus 6 farads. Now times, now what's the voltage of the, so now because the switch is open, the voltage across each capacitor is the same because there's no current, so there's no voltage drop across the resistors. So it's 18 volts. So 18, I'll put in the significant figures this time to make sure that that's carried along. 18 volts, which gives the charge, initial charge on A of 5.40 times 10 to the minus 5 coulombs. All right, it's pretty straightforward calculation here. Now the initial charge on capacitor B, we'll call this B, I for initial. So again, capacitor A, capacitor B, we'll call that voltage A to keep this more straightforward so we don't get lost. Voltage B, so this guy is 6 microfarads, 6.00 times 10 to the minus 6, sorry, not coulombs, farads, times, again, 18 volts. 18.0 volts. Significant figures are very important. Let's see here. So that's going to be equal to 6 times 10 to the minus 6 times 18. So that gives you 1.08. 1.08 times 10 to the minus 4 coulombs. All right, so now that's the initial. So this is assuming that both the circuit has been, the switch has been open long enough for both capacitors to be fully charged. So that's what they're going to be. Now, if we close the switch and we wait enough time based on the RC time constant between the resistor and the capacitor to allow the capacitors to be fully discharged, so we can say now the QF, I'm sorry, so QA F is going to be equal to CA times VA, which is going to be equal to, again, 3.00 times 10 to the minus 6 farads. Now here you got to watch out. So the voltage now, because the circuit is closed, there's now a voltage drop across these resistors. So the voltage drop across resistors for A is just going to be the difference between, so it's going to be, so the voltage drop, we've already found that the voltage drop across this guy is 6 volts. Now the voltage drop across this guy is going to be 12 volts because you have 18 volts and it has to be 18 volts. So you have, so now the voltage across this capacitor is going to be 6, time, so you have 18 volt, 18.0 volts, minus, 12 volts, which is the voltage drop across this resistor. 12, I keep doing that. 0.0 volts, which is going to be equal to, which of course is just 6 volts. So that's going to be equal to 1.8 times 10 to the minus 0.80 times 10 to the minus 5 coulombs, sorry, not farads, coulombs. And now QB final is equal to CB times VB, which is equal to, where is it at here? Yep, there we go, sorry. 6.00 times 10 to the minus 6 farads times the voltage across, drop the voltage across that capacitor is going to be 18.0 volts minus 6 volts. Since we've already figured out in the previous problem that's 6 volts, which is going to be 7.2 times 10 to the minus 5. 10 to the minus 5 coulombs. All right, so now I'm going to add one more page here so we can look at the difference between the final and initial and final for both capacitors. So QA final minus QA initial is going to be equal to 1.80 times 10 to the minus 5 coulombs minus 5.40 times 10 to the minus 5 coulombs, which is just going to be equal to 3.60 times 10 to the minus 5 coulombs. And QB final minus QA QB, here, let's just do this. QB initial is going to be equal to 7.2 times 10 to the minus 5 coulombs minus 1.08. That doesn't look very good. Times 10 to the minus 4 coulombs, which is just 10.8 times 10 to the minus 5 coulombs. So that is also equal to 3.60 times 10 to the minus 5 coulombs. So the charge drop when the circuit is closed is the same from both capacitors. So looking at the physics of this problem, when the switch is open, the current will decrease until the capacitors are fully charged, at which point no current flows and the circuit is in an equilibrium state. When the switch is closed, the current is allowed to flow through the resistors, and this will then cause capacitors to discharge. All right, thank you.